Okay, hello everybody. Uh, my name is Mahmoud Samman. I am the president of Houston Engineering Solutions, and I'll be talking about the three main challenges facing industry on coke drum reliability. I have been working in this area for about 30 years, and this is my appraisal of these challenges that I would like to share with you. So the overview, those three challenges are the one-shot inspection approach, the smoothing of laser scans, and the acceptance standard for weld overlay finish. First, we'll talk about the one-shot inspection approach. So cracks in coke drums are not all the same. There are three distinct type of cracks that we see in coke drums. One of them is induced by excessive bulging. Another one is related to welds, most commonly circumferential welds, and that includes the stress risers, material mismatch, and weld defects. And the third type is the one related to aging. So just to preface this discussion, just keep in mind that not all cracks are the same, and each one can develop at different parts of the drum life and different locations. So they're different both temporally and over time and spatially and temporally. There are also different types of bulges. So we talked about cracks that can develop due to excessive bulging. Well, not all bulges are also the same. We have a paper that we talk about this in detail. There are 9 different types. They're also caused by different mechanisms, different locations. Well, with that in mind, how can we operate coke drums reliably? Well, this is our inspection toolbox. There are 2 primary toolkits that we use. One of them is dimensional measurements, and the second is crack detection. So dimensional measurements is used to provide a basis for assessment of bulges, which we use to predict failures and perform preemptive bulge repairs. There's only one tool that we use for that purpose, and that is laser scanning. It's a tool that we've used for over 30 years. It's very effective at quantifying bulges and performing these tasks, the assessment, predicting failures, and performing preemptive bulge repairs. Now, the second toolkit is the one that we use for detection of cracks. Well, there are 2 groups within that kit. There are the methods that we use for single-sided inspection, and there is one that we use for dual-sided inspection. What that means is the first set of tools, namely visual inspection, liquid penetrant testing, and ACFM, these methods can only inspect one side of the wall. The other 2 methods, advanced ultrasonic testing and acoustic emission testing, these are the methods that can be used to inspect both sides of the wall. And this is really very important distinction, because if we're operating a coke drum, it's not enough to inspect one side of the wall. because cracks can develop both on the inside and on the outside surface of that wall. Advanced ultrasonic testing methods, such as time of flight and phased array, can be used usually from the outside, but in general can be used from both sides of the wall to inspect the drum for cracks on either side. Acoustic emission testing it does the same thing, but it's more of a global test method that allows us to detect and locate cracks anywhere on the drum while it is in operation. So the purpose of these crack detection methods is to find and size active cracks in coke drums on both sides of the wall. Once we do that, once we know where these active cracks are located and size them, determine how long and how deep these cracks are, we can perform crack repairs in a timely manner. Now, I am underscoring the word active cracks because quite often in coke drums, coke drum may be fabricated 50 years ago, and during fabrication, there's a little weld defect or a crack that developed during the fabrication process, but that crack stayed constant, stayed steady. It did not increase in size for 50 years. So when we are at a point of performing crack repairs, it's important that we make sure that we are repairing an active crack, a crack that is growing, that can pose a threat to the mechanical integrity of the drum, as opposed to a passive crack that has been there for 40 years. With those two toolkits, the dimensional measurements and crack detection, we can ensure that a coke drum is reliable to operate, that we would not have to shut down unexpectedly during operation because of a steam cloud, because of loss of containment, and having to disrupt the operation to perform needed repairs. So what is the problem? The problem is, I have noticed over the years that in many cases, companies tend to impose a limit on themselves of basically because of budget constraints and limited downtime. They say we can only use one of those two approaches. We either use laser scanning or crack detection methods. And that is very challenging because neither one of those two inspection methods is sufficient to detect and predict failure in a timely manner. So if we use laser scanning, it would alert us to bulges that are getting severe enough to cause cracks. And that is very helpful for making plans to repair those bulges before they get to develop those through-wall cracks and interrupt operation. But that would not tell me anything about cracks that are developing at circumferential welds, for example, due to fabrication defect, or due to stress risers that have initiated cracks and allowed those cracks to propagate over the last 10 or 20 years. And vice versa, if I were to use crack detection methods only, I would not be able to determine how severe my bulges are and whether I can run between turnarounds without an unplanned disruption. the cause, and I've seen this in many cases, is that we get unpleasant surprises. And a lot of times management is disappointed because, here we are, well, we're using this one method to inspect coke drums, and then we get this through wall leak and stop the operation, totally blindsided. Well, the problem is that we're using the one-shot approach, just one method only. What is the fix for that? Is we have to recognize that one shot, that one method is not enough to predict all these different types of failures, that really both methods are necessary. Okay, so now to the next challenge that we see, which is the smoothing of laser scans. So for those who are not familiar with laser scanning, well, when we go into coke drums to perform a laser inspection, in most cases, we either use the drill stem or we use a tripod and lower those laser scanners inside coke drums in order for us to perform that laser scan. Well, what happens is when you do that is we usually experience a lot of vibrations. The drill stem can vibrate significantly because of the way it's a long, slender member that is exposed to vibrations. And quite often it goes into resonance. Some of those vibrations can be so severe that the data becomes virtually useless. There is also the issue of digital noise, and that can initiate from the hardware that is used to perform the scanning. Some types of electronics and hardware used for that scanning process can generate substantial amount of noise in the data. So just to give you an idea, in this chart, if the bulge looks like that red line that you see on this chart, and the vibration signal looks like that blue line that you see on this chart, if you add the two, you get the black line, which represents the wall profile plus the vibration effect. So when you perform the scan, you get the black line, not the red line. Let me show you what that actually looks like in the field. So in this slide, this is an actual scan of a coke drum, and what you see in the left two photos is the scan data, the zoom in of the scan data that shows the effect of vibration. You see those ripples on the top and bottom photos. These ripples are not real. So if you get this laser scan, assuming that this is what your drum looks like, you'll be surprised, because you will look at this and you wouldn't be able to understand why the drum looks so wavy. In reality, it is not the drum, it is the vibration that the laser scanner observed or was subjected to during the scan. Well, so what happens next? Well, sometimes smoothing is used to get rid of that ripple effect caused by vibration and noise. And what you see in this slide is the outcome of different levels of smoothing. So if you take a moving average smoothing method, you get different outcomes depending on how much smoothing you perform. If you use a moving average of 3 points, you get one line. If you use a moving average of 31 points, for example, you get a totally different profile. And as this chart shows, with that same example that I provided earlier, the shape of that bulge can significantly change depending on which smoothing method you use. Well, based on that, if I were to zoom in at the peak of the bulge, you will see that the wall shown in red here, and see how it compares to the signal that we measured, which is in black, that total curve, and then the different possibilities of profiles that depend on how much smoothing we performed on that signal. So instead of getting that red profile, which is the true profile, you get one of those depending on which smoothing method was used by the laser scanning company. Well, this causes a lot of problems for us because when it's time to perform the bulging assessment, which is the main purpose of laser scanning is just a measurement tool. It is not an engineering assessment. So we take that data and we run it to determine how bad those bulges are. If you look at this case study, the radius map with less smoothing and more smoothing, if you look at those two, it may not be obvious that you have a big difference just by looking at the radius. The radius of the two maps, they are kind of similar. So what happens when we perform our plastic strain index assessment of bulges? Well, this is what we get. These are the two maps of PSI of those two scans that I showed you earlier. So the one with less smoothing is on the left, the one with more smoothing is on the right. And if you look at the color contour, you will notice that bulges in the less smoothed lasers from the less smooth laser scan are significantly higher in severity than those that we get from the more smoothed laser scan. So while a smoother laser scan looks nicer, when you look at it, it has less spikes and spurious data. From an engineering standpoint, it can completely undermine the accuracy of the assessment. In several cases that we have looked at, we got those laser scans that have been smoothed, and we don't know how much smoothing was done to them. We know that it is inconsistent, and it varies from area to area. And so we look at them and we performed the bulging assessment, and we see there is no problem. The bulging severity was very low. And then we find out that there is an actual through-wall crack that had developed recently. And the only reason why we did not capture that is because the laser scan was smoothed so much that the bulge looked so mild. The more you smooth, the milder the bulge looks. And at times we have looked at the trending of these laser scans, and we looked at them over the years, and you see a laser scan showing reduction in bulging severity of all bulges, which is, of course, physically impossible. We can have every once in a while, there is a remote chance that you can develop a favorable hotspot in a coke drum that can improve the severity of bulging, but it is impossible for all bulges in a coke drum to improve over time. These are the clues that alerted us to this problem, and we are still struggling from this because a lot of the laser scans that we receive for assessment have been smoothed in an inconsistent manner. And unfortunately, there's nothing we can do on our end. Once a laser scan is smooth, we have no control over that error anymore. It's an error that is built into the data that causes these unreliable assessments. The third and last one of these challenges is the acceptance standard for weld overlay finish. So those of you who have performed weld overlay repairs, you know that the finish of the weld overlay is not very consistent. In this slide, the right specimen is a specimen that was received as a sample. The one in the middle is the one that was received as a go-by, and the one on the left is an actual weld overlay that was performed on the coke drum. And if you look at the stress risers, the potential for stress risers between those three, it is very, very different. The one on the right has very minimal stress risers. The one in the middle has more stress risers. The one on the left has extremely high, totally unacceptable stress risers. So the question is, once we start performing a weld overlay repair, how do we know that the surface of the weld overlay is acceptable? And what life implications does that have? So, as many of you know, that weld finish is very important for determining fatigue life in any metal. So this is an example of surface grinding, where that weld, you see the weld overlay at the bottom, and for this band, we performed surface grinding, and you see the big difference between the two. One has a lot of, it's as welded, the one at the bottom is as welded, the one on the top is surface ground. And of course, the performance is very different. This is a generic chart that shows the effect of surface finish on fatigue life of metal. So the x-axis is the number of cycles to failure in that specimen, and the y-axis is the cyclic stress. Now, the different curves indicate the amount of sanding that was done to the specimen. And as you see, the finer finish that is shown with the solid black round dots provide us with significantly longer life. For example, take the cyclic stress of 240 megapascal. The least sanded, or the least fine polish, would give us something like 200,000 cycles. The most polished, the finest sanding would give us something like 600,000. So that's an order of three multiple, just because of the amount of sanding or the degree of sanding that was used. So when we go from sanding or polished surfaces to as-welded surfaces, this difference becomes an order of magnitude difference, and therefore it has a significant implication on the life of that weld overlay. So what happens if we do not pay attention to this? If we get these as-welded surfaces and we don't catch these significant stress risers? Well, as you see, these are photos of actual failures that we had in coke drums that were weld overlaid with poor surface finish. These two have actually resulted in through-wall failures in both cases. Now, luckily, this is not a very common problem, but it is a problem that we see as these weld overlays become more popular, and as we see more and more unqualified companies trying to get into this business. So in both cases, as you see, those cracks developed at the stress risers or the grooves between weld passes, the deep grooves that you see there. Well, what is the problem? The problem is that we don't have a rigorous surface inspection tool, and we don't have a standard acceptance criteria. What does that mean? It means that if we send two bona fide inspectors with a lot of experience and we ask them to inspect the surface of the weld overlay, we can have two completely different outcomes. One of the two good inspectors would come back and say, I didn't see anything unusual. It all looks good to me. And the other one would say, oh, that looks really bad. Some of those grooves appear to be really unacceptable. Well, the problem is we cannot determine which one is correct without a robust method to inspect and a recognized acceptance criteria. So what does that do to us? It makes those surface finish failures more likely to occur. So the options we have is we either have to grind to ensure that we don't have any of those stress risers behind, or find a way to standardize this process so that we can ensure that a weld overlay performs as expected. Well, that brings me to the conclusion of the presentation. Just to recap, we talked about 3 industry challenges. One of them is that one-shot inspection approach, where we use either laser scanning or crack detection methods and hope that that would be sufficient. The second one is the smoothing of laser scans that makes it very difficult to perform accurate engineering assessment of bulges in coke drums. And then the third was the lack of acceptance standards for weld overlay finish, and why a poorly executed weld overlay can lead to premature failure. With that, I'm open to any questions that you may have.